Imagine I have a beautiful book filled with captivating stories, and I asked myself, what is the book made of? Well, I need to look deep inside the book, so I magnify it. And if I keep on doing it deep inside, sooner or later, I begin to see fibers of paper. When I zoom it further, I begin to see molecules. I can enlarge them, and if I make them big enough deep inside, I begin to see atoms. And this is not the end of the story because we have electrons zooming around the nucleus. Deep inside, mostly empty space is the atom. But if I zoom in further, I see the nucleus. If I grab the nucleus and magnify it, I see it is made of further particles, which we call neutrons and protons. And if I grab one of the neutrons and magnify it, I find yet further particles known as little tiny quarks. Now, here is where the conventional idea stopped. String theory comes along and suggests that inside these particles there is something else. So if I take a little quark and magnify it, conventional wisdom says that there is nothing inside. But string theory says I'll find a little tiny filament of energy. Just like a string on a violin, if I pluck it, it vibrates and creates a little musical note. The string in the string theory, when they vibrate, they don't produce musical notes, they produce the particles themselves. So right now, what a quark is, nothing but a string vibrating in one pattern, and what an electron is, nothing but a string vibrating in a different pattern. So my question is, what is a neutrino? That you have to answer yourself. So if I take all them back together, I have my ordinary book. And if these ideas are right, they are speculative, but if they are right, deep inside a book or any other piece of matter, there is nothing but a dancing, vibrating cosmic symphony of strings. And this is the basic elementary idea of string theory. The long search for theory of everything, approximately 400 years ago, Galileo started piecing together the basic principles of reality. Now we call them the modern science. But the question he was trying to answer is as old as humanity itself. What are we made of? What are the fundamental building blocks of the universe from which you, me, the stars, and everything is constructed? In the centuries since Galileo, thousands of experiments and theories have peered into smaller and smaller distances, converging on a single picture of structure of matter. The standard model, this somewhat daunting looking formula, is where we end up. It gives the correct answer to hundreds of thousands of experiments, in some cases with an accuracy that is unprecedented in science. It is, by name any measure, the most successful scientific theory of all time. And yet, for something so extraordinary, we give it a rubbish name. We call it standard model. To understand the standard model, it is more convenient to use the language of particles, fermions and bosons. As we build up the standard model, we are going to meet lots of particles with an array of names that can vary quickly and become believing. But there is one classification that is the most important. Every particle is either a fermion, which is a matter particle, or a boson, which is a force particle. The distinction between fermions and bosons lies in the quantum world. Fermions must be something which is called as Pauli's exclusion principle. Roughly speaking, this means that you cannot put two fermions on top of each other in space, as these are the building blocks of matter. On the other hand, you can pile on top of each other as much as they want because they are totally unconstrained by Pauli's exclusion principle. Bosons are the particles that can mediate the forces. We'll talk about two more later, but for now, let's start looking at by fermions. Electrons and quarks, protons and neutrons. Everything that we are made of can be reduced to just three matter particles known as an electron and two species of quarks known as up quark and down quark. The familiar proton and neutron contains total three quarks in them. The proton has two up quark and a down, while the neutron has two down quarks and an up. Put protons and neutrons together and you will have a nucleus. Add electrons in nucleus and you will have an atom. Put a bunch of atoms together and that's what you're made of. All the beauty and complexity that we see in the world around us can be traced to some collection of three particles rearranged over and over again in different combinations. Neutrinos next come. In the fourth type of matter particle, it's called neutrino, and it's not like others. Neutrinos are extremely light and barely interact with anything else. For example, in the time it took me to see this, something like 100 trillion neutrinos passed through your body. Most of them came from sun, and many of them have been streaming through the universe uninterpreted since the first few seconds after Big Bang. So there we have it, four matter particles. Three of them make up you, me and everything that we know around us, and very peculiar cosmic ghost flowing through all of us, muons and taus. 4 is a nice number, isn't it? But here is where things start to get weird, because nature didn't stop there. For the reason that we don't understand, nature took this collection of 4 particles and made 2 further copies. This means that there are actually 3 different kinds of electron-like particles. The electron that we know today, there are particles called muon and the tau. The muon and the tau behave exactly like an electron, with one most important exception: they are heavier. The muon is almost 200 times heavier than the electron. The tau is almost 3,500 times heavier. Strange and bottom quark, charm and top quark, these are the generational patterns that repeat for the quarks. There are 2 heavier versions of quarks called as strange and bottom quark, 2 heavier versions of up quark called as charm and top quark, and there are 2 more neutrinos. We become slightly unimaginative in naming electron neutrinos, muon neutrinos and tau neutrinos, and call the full collection of neutrino. We don't see the second and third generations of particles in everyday life. Then how do we detect these elusive particles? The answer is, we can create these heavy particles, but they are unstable. This means they will quickly decay into first generations of particles that we are made of: electron, up quark or down quark. Nonetheless, we know they exist. We can detect these particles in particle accelerators. In some cases, we have even been able to take photographs of the tracks they leave behind. So this is the collection of particles that makes up our world. Now the question arises, why do particles come in sets of 4? To understand this, in particular, we understand there is a mathematical consistency conditioned in the standard model that tells us that you cannot have one particle without the other 3. In contrast, we have no idea why there are 3 generations of particles rather than any other number. That's a complete mystery. The direct equation describes all the particles. There is a surprising aspect of mathematical unity. Here, all the particles are described by exactly the same equation. This equation was written down in 1920s by the physicist Paul Dirac, originally to describe the electron. But as we discover more and more electrons and quarks and neutrinos, we realized that they are too described by a Dirac equation or variants of it. In fact, we now know enough to be sure that if we found more matter particles, they too must be described by the same equation, the Dirac's equation, so that the stuff we are made of. But we are still missing something crucial, and that's the forces, the 3 fundamental forces. Without the forces, the universe would be boring. all the particles would wander around in the cosmos like lost souls, never interacting. There are three fundamental forces in the standard model, and these allow us to explain why and what we see around in the universe. Electromagnetism, the strong force, and the weak force. Each of these forces comes with the associated particles. These particles are bosons and the other half of particle family. Bosons are force-carrying particles. In other way of viewing things, you can think of the fermions as swamping bosons between them, affecting their motion and giving rise to what we call a force. Let's begin with the most familiar of these forces, electromagnetism. The photonic electromagnetism is responsible for the chemical properties of the elements, and we have harnessed it to create much of the modern technology. It acts on anything that carries electric charge. And the quarks, but not on the neutrinos, because neutrinos are electrically neutral. An electron sitting in space will give rise to an electric field which spreads rapidly outward and attracts or repels the other electrically charged particles in its neighborhood. But if you look more closely and clearly at the electric field, you will find that it's comprised of a collection of particles called photons. The next is strongest fundamental force in nature, named as strong force. This force acts on only quarks and subsequently on particles like protons and neutrons that are made of quarks. This is the force that holds together the nuclei of atoms. It's also responsible for the nuclear fission and gives the energy that is released in an atomic explosion. Just as the photon, it is associated to electromagnetism. We call it gluon because it literally sticks quark together. Similarly, as the electrons give rise to electric field, so the quarks sitting in space will give rise to gluon field. But something minus can happen. Until electromagnetism, the field doesn't spread out rapidly. Instead, the quark produces a thin flux tube, a string-like object which can only end when it finds different kind of quark. This is what makes a strong force strong, because the two quarks are joined by flux tube. It takes more and more energy to pull them apart. This is why we never see quarks on their own. They are always bound together by force inside bigger particles like protons and neutrons. And this phenomena is called as confinement. Now let's talk about the weak force. The weak force, the radioactive beta decay, W and Z bosons. The third and the final force is the most intricate and subtle of the all forces. This is the weak force. Like the strong force, the weak force acts only on subatomic distances. But rather than bind particles together, the weak force is all about decay. We just learned that the strong force binds quarks together to form protons and neutrons, creating the atomic nucleus. The weak force has the astonishing ability to allow quarks to switch their identities. For example, a down quark can turn into up quark, releasing an electron and neutrino in the process. This means that a neutron can morph into proton. This process is called radioactive beta decay. In this way, the weak force is responsible for the nuclear fusion reactions. Along with, it's important to note that the weak force is the reason that heavier matter particles like muon and the strange quark quickly decay into three lighter and more stable fermions that make up the matter as we know it. The weak force is the only one of the forces that act on all the particles. In particular, it is the only force that neutrinos feel. There are particles associated to weak force, and we call them W and Z bosons. The Higgs boson and the Higgs field. It's finally time for us to meet the last piece of jigsaw. The particle that in many ways we hold standard together. This is the Higgs boson. To explain why Higgs boson is special, I should first tell you a striking fact. None of the fundamental particles in the world have mass. In fact, it is worse that the equations of modern physics prohibits the particles from having any mass. Like the photon are obliged to travel at the speed of light, so why don't matter particles fly around at the speed of light? This is where the Higgs boson comes in. The experimental confirmation of Higgs boson came in 2012 when the Large Hadron Collider at CERN was able to smash protons together to cause a ripple in Higgs field. A ripple, that's the particle we call Higgs boson. So this is standard model, 12 matter particles interacting with 3 forces and a Higgs field. It is beautiful picture. This is the dream of grand unified theory. There are some theoretical signs that this may be the way things work, but no experimental confirmation we have. What else is missing? Of course, we are left with the obvious: how does gravity fit in the picture? Force that is missing: gravity. At the beginning of the video, I talked about the problem of quantum gravity. In recent years, we have discovered gravitational waves, which are ripples of space and time itself. And if we look clearly and closely, there are good reasons to believe that these waves are made out of quantum particles called gravitons, just like light waves are made of photons. But we are a long way from discovering individual graviton experimentally. There are other things missing from the standard model. Where is the missing dark matter and dark energy? It doesn't include the individual realm of dark matter and dark energy, which means we are missing the explanation of moving 95% of energy in the universe. Dark matter, for example, is almost certainly made of additional particles that don't interact with light. Perhaps these particles have their own forces and their own messengers, bosons, and there are still more questions about the unsolved mysteries of standard model. The hope is that with experimental results pointing the way together with new theoretical ideas, we will ultimately be able to reveal the next layers of reality and understand what is beyond the standard model. Until we continue Galileo's journey with the ultimate goal, a theoretical framework to explain the universe in everything. This is the theory of everything.